Okay, this is lab 2-10, unbalanced 3-wire circuits. The objective is to demonstrate that a basic current and voltage relationships in an unbalanced single-phase 3-wire circuit. The purpose of this lab is to demonstrate the properties of an unbalanced 3-wire circuit under normal operating conditions and under faulty neutral conditions. Be aware of these properties should reinforce the importance of trying to keep 3-wire circuits balanced whenever possible. Also be aware of these properties being aware of these properties will help the electrician quickly troubleshoot unbalanced 3-wire circuits and faulty neutral connections. Step 1 is ensure that the main breaker on the power supply is off. Step 2 is use longer leads and connect up the diagram as shown in that figure there, which we've done. So we've got all 3 cone heaters attached now. So we have line 1 coming to this guy. This is my neutral point here, and then on this side between the line 2 and neutral we've got 2 cone heaters. So now we're showing that we've got 2 in series with each other across a 110, but it's technically 120 is what we're going for, and then 120 across the cone heater 1. All right. They said using the 660 watt 120 volt rating of the cone heaters, calculate the nominal resistance of each cone heater. So that's 22 ohms using the R is equal to E squared over P like we did in the previous lab. And then we expected to calculate current in this circumstance. So my calculated current, based on a drawing that I will go through in the Learning Hub with you, anticipating 120 out of here, which I know we're not going to get, but I calculated it based on that anyways. I estimated the 5.45 amps flowing to this cone heater, okay? But then because the resistance up here is the 22 plus the 22, so 44 ohms between line 2 and neutral, my current is going to be halved. So that's roughly 2.7 amps, okay? So I see 2.7 on the line 2, 5.4 on the line 1, and then another 2.7 coming back on the neutral because it's unbalanced, okay? I know my actual values are going to be much different than that because the voltage we're going to see is not going to be anywhere near 120, but that's what I've calculated for, okay? Next would be to energize, and then we'll take some measurements. So I'm going to power up. We are seeing 212 volts roughly now. We're getting some fluctuation in the spool here a little bit. Okay. So they're asking for a line 1 to neutral. So we're going to go line 1 to neutral, and I should see the 10, well, we're down now, 103 there. And the line 2 to neutral is 109. So already we're a little bit unbalanced just in general. 103 and 109. Okay, and then line 1 to line 2 should be the 212, which it is. Okay, then they want the voltages at cone heater 1, which is up here. So there to there, we're seeing 103 again. And then cone heater 2 plus 3, which would be this point to that point, should be the 109, which it is. Okay, and then they want our currents. Now keep in mind this is unbalanced, so I should have current on my neutral. So I'm just going to turn this guy on again to AC amps. I'm going to measure my current from line 1. I estimated 5.5 or 5.4, but it's actually 4.7 on the line 1. Okay, and on my line 2, I've got 2.4. Coming back. So the difference between 4.7 and 2.4 is 2.3. So my neutral should see somewhere around 2.3, which in this case is actually saying 2.1. Oh, hang on, we're still thinking about it for a minute. 2.1. So the math's not adding up exactly correct, but we're pretty close. Because remember, these meters round a little bit. Okay, so I'm going to call it 2.2. Yeah, we'll just go with this, okay, or go with that. So realistically, the unbalanced current is coming back on that neutral circuit, or on that neutral, okay? Then what they want us to do is de-energize that. We're going to shift this neutral over to our light bulb again. I need a longer jack there. Okay. Guess I could have left that guy up there. So there's my neutral. And this point here, okay, going to there. Now keep in mind, I know that I have current on this neutral, so the element in that light bulb should light up a little bit, okay, proving that there is current flow on that neutral. Power up, and you can see we have current on the neutral because that 200 watt light bulb is lit up, okay. My source voltages, all of those voltages should be exactly the same as what we did before, so I'm not going to waste the film time in talking about that, okay. Well, I guess we could. The line 1 to neutral, might as well do the lab correctly. Line 1 to neutral. We've got the 105 now, so it's changed a little bit, or 106. This is 107 or 106. We're fluctuating up and down a bit. Line to line, we're sitting near 213 now. So we are jumping up a teeny little bit here. So we'll call them 106 each, and then 212 for our total. Okay, and then our cone heater loads will once again be the 106. Whoops. No, we're not. Where are we there? Why do we got 80 there? Got 80 there. And then across here, 132. Okay, what are we seeing there for? Sorry, I'm just thinking aloud here. Okay, I'll have to work that out and do some math here. All right. Oh, I know why. Because this guy is actually looking at a little voltage drop across that lamp too. So we've created a bit of a combination circuit within here. Okay. More importantly, I'm not going to sweat that stuff. I want to look at and look at our currents once again. Okay. Remember we thought we'd see about 4.5. It's actually changed a little bit. It's 3.8. Okay. And this guy is sitting at 3. So now our light bulb should be sitting at the 0.8, which it is. Okay. So by adding that light bulb in play, it changed the circuit a little bit. Okay. But once again, the proof is to prove that there's actually current flowing on that neutral. Okay. So what did we say? We said 3.8 on line 1, 3 amps on line 2, and 0.8 on our neutral. Okay? I know that differed from the previous one. Sometimes it's hard to replicate what we do on the board in this circumstance, in particular because we are also reliant on an auto transformer to transform our 3-phase system into our single phase. So there's some inefficiencies there. The next thing that we can look at here is they ask us in the next step to open up that neutral again. Now we know that we have an unbalanced circuit. Okay? Here's where I really want to prove the math. Okay, I'm going to power back up again. Hopefully by opening that neutral up, things should sort of rectify themselves a little bit. Okay, so across the cone heater 1, now we're sitting at 71. And then these guys are sitting at 140. Okay, so if we called it 70 and 140, just trying to do some easy math, and then line to line across the whole thing, we got 213. The voltage across the neutral, or that open, we should see the difference between 70 and 213. Or sorry, what are we going to see? The difference between I'm just trying to think. We're going to see the difference between our 110, which would have normally been here. So our 107 is our line to neutrals. So we're at 107 and 107 from line to neutrals. So my open here should be the difference between the 70 and the 107, or the 40 and the 107 roughly. Okay, I know we're not exactly clear there. It should be about 30 some odd volts. Okay, so let's just measure that and see if our difference is going to be there. And we got 36 volts there. So that's the voltage across the neutral there. Okay, or across the break. And I know we've done a lot of that in our worksheets before. Okay, so that sort of proves that the math does work out pretty well. The next thing they ask us to do is obviously clean up, and then we'll talk about this in the Learning Hub. Okay, so that was Lab 2-10, unbalanced 3-wire circuits. I apologize that the numbers don't perfectly add up the way that we want them, but we can only deal with the way we can deal with it. Okay, so that's Lab 210.